This mini-documentary traces the development of theories and models that led to our modern view of the solar system. This whirlwind tour of ideas spans over 2,000 years and is by no means a complete recounting of history, merely a brief introduction to the story that would set the stage for the development of our modern scientific practice and for the disciplines of physics and astronomy. Our story begins with a man named Aristotle. Aristotle lived from 384 to 322 BCE and emphasized the observation of nature and the use of logic to interpret nature. He believed these principles formed the foundation of science. Our modern logic methods were standardized and published by Aristotle. He did not believe in experimentation on the grounds that inescapable observational errors made experimentation imperfect and thus not worthy, and also because experimentation involved working with your hands, which was work for slaves in the lower classes, who according to him were, by nature, not trustworthy. He believed that logic, on the other hand, was for the upper classes and was more pure. So what did Aristotle's logic and observations cause him to conclude? Aristotle observed that the earth was unmoving, or at least could not be felt to move. He reasoned that the earth was the center of the universe. This idea was supported by looking to the heavens. The stars seemed to move across the night sky in a great arc. They always move together, in patterns that do not seem to change. Observing and tracking these patterns led to the development of constellations. It should be noted that constellations vary from culture to culture and across history, and that they are merely used to help track the motions of the stars. If it is assumed that the sun, the moon, and the stars are mounted on great enclosing spheres that rotate around the earth, you can explain almost everything seen in nature when looking towards the heavens. Aristotle's picture showing the order of the universe is shown here with the earth at its center, and the sun, moon, and stars moving about the earth in orderly fashion with a few notable exceptions. A few stars seem to wander around in a pattern of odd, complex loops. The Greeks called these by a word we now know as planet, which means wanderer. Aristotle's universe only included the 5 planets that were observable with the naked eye. A new planet, Uranus, would not be discovered until 1781 by William Herschel with the aid of a telescope. To explain the strange motions of the planets, Aristotle and others before him said stars are mounted on spheres and that the planets on disks that rotate. The combination gives the planets a looping path. This gives a rough explanation for what was observed. As time went on, many yearned for a way to predict the motions of the planets. A man named Claudius Ptolemy, who was a citizen of the Roman Empire, of Greek descent, and who lived from 90 to 169 AD in Alexandria, Egypt, took up the challenge. Ptolemy worked out the details of a theory explaining planetary motion by placing them on disks, mounted on disks, and so forth, that became known as epicycles. The theory, however incredibly complex, fits observed planetary behavior. For data, he used the Babylonian list of kings, which is a huge data set collected over a period of hundreds of years by astrologers, listing when kings were born and where the planets were in the sky at that time. Although not very precise, this list went back hundreds of years, so Ptolemy's theory could be fine-tuned to an amazing degree. Here we see the apparent motion of Venus tracked across the night sky from a stationary Earth. Most of the motions of Venus is along the direction of the stars, or prograde, while part of the motion appears to move in opposition to the stars, or retrograde. These motions are explained by placing Venus on a rotating disk or epicycle, which allows its motions to be predicted. The sun moving about the Earth is also shown for reference. As we can see here, the motions of Mars can also be described using Ptolemy's epicycle theory, and fits the available data, not perfectly, but quite well. The same can be said for applying epicycles to describe the motions of all the planets visible to the naked eye. As many would agree, Ptolemy's model when applied to all the visible planets is very complicated. Furthermore, epicycles to explain retrograde motion did not lend itself to understanding anything else about what is happening in the sky. Despite these limitations, Ptolemy's explanation of Aristotle's interpretation of the universe lasted for 1,300 years. One of the first to go on record challenging the views of Aristotle and Ptolemy was a Polish astronomer named Nicholas Copernicus, who lived from 1473 to 1543. He is credited with proposing the heliocentric, or sun-centered model of the universe. Although not a correct description of the universe, his ideas spawned a revolution of thought and ideas that eventually led to what is now considered modern science. Copernicus thought that a simpler idea was to imagine the planets orbiting the sun instead of the Earth. His idea was so much simpler than epicycles that scholars were attracted to it despite the danger of opposing the established orthodoxy and the unusualness of the idea. His idea did not gain much attention or traction until after his death, and his book called De Revolutionibus was not published until 1543 when he was practically on his deathbed. Here the motions of Mars are shown from the heliocentric model proposed by Copernicus. The apparent position of the planet is explained due to both its and the Earth's position relative to the Sun, which has been placed at the center of the universe. Copernicus has merely reinterpreted the observational data used by Ptolemy to propose a new model of the universe. A side-by-side comparison of the geocentric and heliocentric models demonstrates the relative simplicity of the heliocentric model, but it must be noted that since Copernicus assumed circular orbits, which is not quite true, his model really did no better with the older data of the Babylonian list of kings than Ptolemy's model did. The truth of the solar system will require more accurate data and a deeper analysis of that data. The challenge of collecting more accurate data to reveal the truth of the solar system was undertaken by this man, Tycho Brahe, who lived from 1546 to 1601. He was a master at securing patronage for his research, and is best known for collecting the most extensive and comprehensive data on the motions of the stars and planets of his time. His data was collected over nearly 3 decades, and although his personal view as to whether the universe was heliocentric or geocentric is not definitely known, publicly he supported an Earth-centered universe, though this view differed somewhat from that of Aristotle and Ptolemy. Brahe supported a view of the universe that kept the Earth at its center, kept the stars and sun in orbit of the Earth, but placed the planets in orbit around the sun. This view was somewhat of a compromise between the Ptolemaic and Copernican models. Despite being profoundly gifted at and diligent with data collection, Brahe had limited mathematical skills. Perhaps Brahe's greatest discovery came when he hired Johannes Kepler to work with him for the purpose of helping to prove his model, which, as history would have it, never came to fruition. Johannes Kepler, who lived from 1571 to 1630, was a mathematician, astronomer, and astrologer. The model of planetary motion developed by Kepler is almost exactly the same as our modern view of the solar system. His mathematical explanations of the motions of the planets paved the way for Sir Isaac Newton's revolutionary and groundbreaking work in the field of science that we now know as classical physics. Kepler formulated his laws of planetary motion using data inherited from his former employer, Tycho Brahe, and Kepler's laws of planetary motion are still used today by physicists and astronomers alike. Using Tycho Brahe's data, Kepler first tried to prove the Copernican view of planets orbiting in perfect circles around the Sun, but it simply did not work. Despite his deep-seated and long-held beliefs in circular orbits, he abandoned the Copernican circular orbit model and ended up with the ellipse as the shape of planetary orbits around the Sun because it is this model that ultimately fit the data. It is important to note that he did not know or care why the planets followed the patterns he discovered, but of equal or even greater importance is that Kepler's new model is based on the principle that in science, theory must give way to evidence, not the other way around. Kepler's model of the planets orbiting in elliptic planes around the Sun was by no means immediately accepted, nor would it be for many years to come. Although a heliocentric model of the universe was gaining steam, further evidence would need to be collected and shared before the geocentric model was abandoned for good. Kepler would not have to wait long, however, for 2 important pieces of evidence were in the process of being discovered that would support his findings and would result in the Earth at last being removed from the center of the universe. A contemporary of Kepler, Galileo Galilei, who lived from 1564 to 1642, has often been referred to as the father of modern science. He made huge strides in the fields of physics, astronomy, and mathematics. Although Galileo never accepted Kepler's model of elliptical orbits, his observations and discoveries supported Copernicus's heliocentric model, which laid the foundation for Kepler to develop his 3 laws of planetary motion. Galileo was an inventor, an artisan, and a craftsman. His ingenuity allowed him to turn a simple spyglass into a modern telescope, and it was with this new scientific instrument that allowed Galileo to make observations that would ultimately disprove the models of the known universe proposed by Aristotle, Ptolemy, and Brahe. When Galileo turned his telescope to Jupiter, he discovered 4 new objects, and when he tracked the motions of these objects, it became apparent that these objects were moving around Jupiter, thus disproving the view of older models where objects could only move around the Earth. These objects would eventually become known as the Galilean moons, Io, Europa, Ganymede, and Callisto. Their names derive from the lovers of the Greek god Zeus. When Galileo looked to Venus through his telescope, he was amazed to discover that Venus underwent phases nearly identical to that of the moon. As he tracked these phases night after night, Galileo was able to conclude that these phases could not be explained by shadows cast on Venus from the Earth. The phases of Venus could be accurately explained when Venus, along with the Earth, were placed in orbit around the Sun, with the phase visible from Earth depending on the relative positions of Earth and Venus in orbit around the Sun. The discoveries of Galileo and Kepler all but put an end to the geocentric model of the universe. Although a heliocentric model for the entire universe proved ultimately incorrect, the heliocentric model of the solar system was on its way to widespread acceptance, and refining this model further led to monumental developments in science, including the law of universal gravitation, general relativity, and so much more, all of which rely on the principle that a scientific theory is only as good as the evidence that supports it. Thank you for watching. I hope you've enjoyed this mini documentary on a history of our view of the solar system.